Hey, welcome back. So now we're getting into the second lecture on polynomial approximation. So last time we saw that Taylor series, while we can actually come up with a nice formula for its remainder and things like that, it turns out it's not really that great of a method of approximating a polynomial. It's used often enough that we want to bring it up and actually mention what you need in order to get convergence, because if people are using it, you better be able to do something with it, or show that it works sometimes. But yeah, on the whole, it's not that great. So there's other methods that people use to approximate functions, and this really depends on context. So Taylor series is a good way to get approximation of the function if you have somewhat decent method of finding its derivatives. But in general, that's not going to be easy to do, or at least not from data sets. So so this next method we're going to talk about over the next 2 or 3 lectures, is that of polynomial interpolation. So polynomial interpolation, basically the idea of this approximation problem is that you have a collection of points, say xi, yi, and you want to come up with a polynomial that will interpolate those points. Now, there's a wide variety of methods to come up with an interpolation polynomial, but we know that if you say have 4 points, then that completely determines a polynomial of degree 3, or 3 points determine a polynomial of degree 2, and so forth. And so if we're trying to interpolate n+1 points, then a polynomial of degree 10 is going to be uniquely defined by those points. Now, I'm going to give you a whole bunch of different algorithms to determine these interpolating polynomials, but as long as we have that degree matching with our data, all of these polynomials are actually going to be the same polynomial, just sort of represented in different ways. And so this is sort of like an idea coming out of linear algebra, where you are trying to represent the same polynomial in the vector space of polynomials with different basis sets. And so initially what we're going to do is, in this first lecture, we're going to go over Newton's method and his divided differences for interpolation. We're also going to talk about Lagrange interpolating in polynomials, which are actually rather straightforward to get your hands on. Newton's method is a little bit more involved in these divided differences. It can get to be a little cumbersome to compute, but with a computer it's not that bad. Then finally, I think in the next lecture, I'm going to relate this back to a linear algebra, and that's going to be using the van der Waals matrix, and then we'll actually prove some convergence results for interpolation, and also look at an example where interpolation doesn't work out very well, or at least not for uniformly spaced points. Okay, so we're going to go ahead and jump into it, and this time we're going to talk about Newton's interpolating polynomials as well as Lagrange interpolating polynomials. All right, see you there. Okay, so let's go ahead and jump into this. So let's talk about the problem that we're trying to handle. And so again, we're doing sort of a polynomial approximation of a function of a continuous function, and usually it's continuously differentiable, but it's going to be, say, a function over an interval a, b to r. And so here we're approaching it through interpolation, and it's going to be the first of several interpolation. It's going to be the first of several lectures on interpolation that we're going to talk about. So let's go ahead and talk about the problem. So what are we given? So before with Taylor polynomials, we were given derivatives. If we knew a certain number of derivatives at a certain point, then we can come up with some approximation of the function using Taylor polynomials. Here, we're not going to be talking about values at a single point, but rather a collection of points that we sampled from the function itself. So we're going to be given these points xi and f of xi, for I going from, say, 1 to, say, m. Well, let's say n plus 1. And the goal is to find a polynomial of degree n such that we have p of xi. I'm just going to write yi, where we write yi is equal to f of xi. For I being 1 up to n plus 1. Okay, and so that's the goal. The first thing we should do, well, let's introduce some notation. We're going to let big pi of n denote the collection of polynomials over the reals with degree at most n. Okay. Now a theorem, and this is coming out of the Stoller book, says that for n plus 1 arbitrary support points, what he means here is xi. So this is written as xi comma yi for I going from 1 up to n. There exists a unique polynomial p in big pi of n such that we have p of xi is equal to yi for I equal 1, 2, up to n plus 1. Okay, and so it turns out that if we can find an interpolating polynomial of degree at most n that interpolates n plus 1 data points, then there is only one polynomial that does that. So in this lecture, what we're going to do is we're going to have several different ways of finding a polynomial of degree n that interpolates n plus 1 points, but you should know that in the end, this is just different ways of representing the same exact quantity. So let's take a look. And now we're going to change to blue, because I'm feeling blue. No, I'm not feeling blue. I'm just feeling the color blue. Anyway, so let's go ahead and talk about existence real quick, and that's actually the easiest thing to do. So here we're going to introduce one polynomial interpolation problem and algorithm, and this is we're going to use Lagrange interpolating polynomials. Right. So given this collection of xi, yi, I going from 1 to n plus 1, we're going to write L sub I at x, and we're going to express it this way. It is going to be x minus x1 all the way up to x minus xi minus 1 times x minus xi plus 1 all the way up to, let's move this over here, go to x minus xn plus 1.
And now on the bottom, what I'm going to have is I'm going to have xi minus x1 all the way up to these guys, xi minus xi minus 1, and then xi minus xi plus 1, all the way up to xi minus xn plus 1. Okay, so what's so special about this function? And this is going to be for I going from, say, 1 up to n plus 1. Well, if I plug in Li of, say, xj, if I plug in anything but xi, it's going to be one of these guys, and it's going to give us a 0. So 0 if I is not equal to j. And if I put in xi, then we're going to get xi minus x1 here, but that cancels with this guy and leaves 1. We get xi minus 1, and that cancels here, and it's going to give us 1. And etc. This ratio is going to give us 1 there, and this one here is going to give us ratio 1 there. So it's going to be 1 if I is equal to j. All right? And we can see that the degree of Li is equal to n. There we go. We can see it's n because we have 1 to n plus 1 points, but then we're subtracting 1 of them out of the middle. So there's n terms altogether, and so the degree of Li is n. So now if we want to interpolate, we can just use a little bit of linear algebra reasoning. And so my interpolating polynomial, p of x, then is going to be this. It is going to be y1 times L1 of x, sum up to yn plus 1 of Ln plus 1 of x. And then you can see that this is going to give us exactly what we're looking for. Because if I put in, say, p of xj, or just say xi, then what is that going to leave me? Well, if it's basically just going to leave me with y1 times 0 all the way up to yi times 1 plus yi plus 1 times 0 plus everything else yn plus 1 times 0, assuming xi is not 1 or n plus 1. And so basically everything else dies away, and all you're left with is yi times 1, and so this is just going to give me yi. And so we see that this is a polynomial that interpolates this set of points. Okay, what does that look like? Well, I mean, you can think of, say, if it was just 2 points, then we'd have a line that interpolated them. If it was 3 points, we'd end up with a parabola that interpolate those points, and 4 points, we'd end up with a cubic, and etc. And so these are the polynomials that we're making. So these are using the Lagrange interpolating polynomials. Okay, so there we go. Existence is done. Uniqueness is not so hard. Basically, what we're going to have is that we're going to suppose that P and Q are in pi n, and interpolate the points xi, yi, I going from 1 to n plus 1. So what we can do then is we can take a look at their difference. So we're going to let r be equal to p minus q. Then we have that r of ri is equal to p of, r of xi is equal to p of xi minus q of xi. And so, but each of these guys are equal to yi minus yi is equal to 0. So we see that Ri has n plus 1 zeros and is a polynomial of degree n. Okay, so what does that mean? Well, basically, in short, that means that R of x, since it is a polynomial of degree n, can be written as x minus x1 all the way up to x minus xn, and so because we know it's 0 at each one of these points, but that only covers n. This is the polynomial degree n, and so the only other free variable here is going to be out of the a, and so if we have n plus 1 points that are making it 0, then that means that a must be equal to 0 as well. And so this is the 0 polynomial. Thus, we have p of x is equal to q of x, and there we have uniqueness. Okay, so we'll stop there, and then we'll talk about another method of interpolation. So the first method we had was writing Lagrange interpolating polynomials, and these are really handy, and they're actually used. But there are other kinds of interpolating polynomials that we can talk about. And really, like I was saying before, this is just a change in form rather than being an explicitly different polynomial. So the other way to do it is using Newton's interpolation formula. Okay. So let's go ahead and talk about it. Newton's interpolating formula is basically based on these extra little polynomials, and we'll have these like tiny, we'll call them n's of j. So n's of j is going to basically be the product of I going from, say, 1 to say j minus 2. Is that what I want? No, 1 to j of x minus xi. Okay, so what do we know about it? So nj of x, say putting in some other value, k, is going to be equal to 0 for k being equal to, say, 1, 2, all the way up to j. And then after that, it's whatever the value is. Okay. There's also one other part that we should talk about, and that is we're going to set n equals 0 to just be the constant function 1. All right, now this all together, we're going to have the sum n equals n of x is equal to the sum of j going from 0 up to n plus 1. And this is going to give me a collection of coefficients, aj times nj of x. And this is Newton's interpolating polynomial. And so this leaves you with asking, what are the aj's? Okay, this is going to lead us into what were called Newton's divided differences. it's not too hard to derive what aj has to be. And we just use the fact that basically for any xi, most of the nj's are going to be 0. So for instance, if I take a look at n of, say, x1, well, we know that this is going to be a naught times n naught of x plus x1 times a1 times n1 x1 plus a2 times n2 x2 and so forth. But we just said above that most of these guys are going to be 0 at x1. So this is 0 and this is 0. And so, so then what that leaves me with is it just tells me that n of x1 should be equal to a naught times n naught of x1, but then again, that was just 1, and we know that this n of x1, if this is an interpolating polynomial, should be equal to just y1. Okay? Okay, so now let's take a look at n2, or nx2. So nx2 is going to give us, well, we know that a naught is already y1, and then we're going to have a 1 of n1 of x2 plus a2 n2 x2, etc. But this is 0, and all those subsequent ones are 0 as well. And so then, and we know that this should ultimately be equal to y2. Now, what is n1? Well, n1 of x2 is going to be, so we have y1 plus a1, and then here we have x2 minus x1 is equal to y2. Thus, that tells us that a1 is equal to y2 minus y1 divided by x2 minus x1. All right. Now, let's go ahead and figure out what nx3 is, or what a3 is, or a2 is using nx3. So nx3 then is going to give us a naught, which we already determined is y1, times n naught, which is just constant function 1, plus now we have y2 minus y1 over x2 minus y2, and now this is going to be times n1 of x3 plus a2 times n2 of x3 and so forth. So then we have plus a3 n3 x3 plus etc. But we know from here on all these terms are 0. So what does that leave me? So it leaves me with y1 plus y2 minus y1 over x2 minus y2. We can put in x3, it's going to be x3 minus x1 this term, plus a2 times, now this is going to be x3 minus x1 times x3 minus x2, and all the other terms are 0, and this should be equal to y3, just by the interpolation property. So now we can figure out what a2 is. So basically, we're going to have a2 is going to be y3 minus y1, and then we're going to have minus y2 minus y1 times x3 minus x1 divided by x2 minus, sorry, that shouldn't have been, let me double check that. Oh, oops, did not mean to erase all those. There we go. x2 minus x1. Yep. So x1 here, x1 there. All right, x1. Okay, so we move these two guys over, and now we need to divide by x3 minus x1 times x3 minus x2. And let's see, what do we get? So we're going to get y3 minus y1 times x2 minus x1 minus y2 minus y1 times x3 minus x1, and all of that divided by x3 minus x1 times x3 minus x2 times x2 minus x1. Right, there you go. And so that's x2. And you can iterate to find other ones. So, iterate. And so that's Newton's divided differences method. It turns out that they satisfy actually a fairly nice recurrence formula. And so if we write if we use this notation, so we write y sub I is equal to yi, and subsequently define, and this is going to be for I being, say, 1 up to n plus 1. And we define successive operations, so we define y sub I up to y sub I plus j, and we define that as y of I plus 1 up to y of I plus j minus y sub I plus 1 up to y sub I plus j, and divide by x of I plus j minus x of I. So this is the recursive definition. Then it turns out that we can write AI so then it turns out we can write AJ is going to be equal to y naught up to yj. Right, and so this is just an algorithm that you need to follow. We can certainly see that it works out for the case of the cases that we've already seen, and yeah, it'd be a good exercise to go ahead and try to implement this term by term. Notice that we initially have j plus 1 terms here, and then we reduce to j terms and j terms. So each time you apply this, you're going to be removing points. So, so given a polynomial, you can either try to work through this recursion, or you can just try to do it by hand this way, and you get the same answers. In any case, so let's see if we can go ahead and try an example with that. Okay, so we're going to go ahead and try to find an interpolating polynomial for the points, say 1, 2, 2, 10, and we're going to have another one, let's call it 3, 5. Okay, so just 1, 2, 3, let's see if we can find this. Okay, so we have 3 points, and so we're going to be looking for a quadratic polynomial to interpolate them. There's a few ways we can do it. One way that we can do it is using the Newton's formula. So n naught of x is equal to 1, and so we have to start off with these basic polynomials. So we have x minus 1, and n2 is of x, is equal to x minus 1 times x minus 2, and that's quadratic. So that tells us that nx should be equal to a naught times n naught, which is just 1, plus a1 times x minus 1, plus a2 times x minus 1 times x minus 2. All right, now n of 1 is going to be a naught plus 0 plus 0, and this should be equal to 2. So that tells us that a naught is equal to 2. And 2 is going to be 2 plus a1 times 2 minus 1 plus 0, and altogether that line should be 10. And so then that tells me that we're going to have a2 is going to be 10 minus 2, and then divided by 2 minus 1, and that's just 8. Okay, so now n3 is equal to 2 plus 8 times 3 minus 1 plus a2 times 3 minus 1 times 3 times 3 minus 2. And so this should be equal to 5. And let's see what we get. So we get n3. We get a2 is equal to 5 minus 2. We get minus 8 times 2, so that's 16. And then we divide by 3 minus 1, so that's 2. And 3 minus 2, which is 1, right? So ultimately, this is going to give me minus 13 over 2. So what we get? Well, we get that nx is equal to 2 plus 8 times x minus 1 minus 13 over 2 times x minus 1 x minus 2. And there we go. Okay, and so that is the interpolating polynomial for these 3 data points. And it's pretty easy to find those coefficients. I just realized that when I wrote this polynomial up here, this really shouldn't be n plus 1, but it should just be n. And yeah, but otherwise nothing else changed here, because we want an n degree polynomial interpolating n plus 1 points. So, but yeah, so that's the idea, and that's how you find Newton's interpolating polynomials. And you've already seen how to find Lagrange interpolating polynomials. I'll put some stuff in the homeworks, and then we'll have a homework video to really go down and do a lot more examples of these. But for now, this gives you the method. All right, we'll pop back to the office.
Okay, well, there you go. So I personally like the Lagrange interpolating polynomials. I think they're pretty neat, being 0 at all the interpolation points except for 1 point where it's just 1. And then you can just scale wherever you need, and then when you add on more of these similar basis functions, they don't affect that point that you wanted to get out of that Lagrange polynomial. So it's a really clever idea by Lagrange to throw that together. And yeah, and as far as quickly putting something together, it works out fairly well. So the but yeah, Newton's method is a little bit more difficult, but it's something you can sort of build as you add 1 point at a time to your interpolating polynomial, and that itself can have some nice advantages. But yeah, anyway, this looks like a good point to stop, and my battery is running low anyway, so I'll go ahead and stop here.